Okay, so there is a possibility though. So consider the array like 1, -3, and 5. Now, including that -3 is like it decreases the sum, right? So even if you wanted to include the whole array, that would be less total sum than just including the 5. Okay, so in particular, the sum is defined by taking any two pairs of indices like I and j, and summing things up from I to j, and then finding the I and j that produces the maximum sum. So I'll give you a minute to think about how to do the brute force solution. All right. So yeah, just take a minute and try to figure out the problem statement and then think about the brute force solution and think about how you might do it using divide and conquer. I think my pencil is out of charge. So I'll start sharing screens again real soon. Sorry about that. Again, if you have any questions, just put it in the chat. Okay, so let's think about this this brute force approach. Okay, so essentially the idea for the brute force approach is to try all possible indices I and j, and then pick the one with the biggest sum. So the question here is, one, how long does it take to calculate, or how many different I and j are there? And for each I and j, how long does it take to calculate the sum, right? So how many different possible choices are there for I and j? Right, so there's n different possibles for I, and for every different choice of I, how many different choices of j are there? So j has to be bigger than I. Okay, let's just say j is bigger than I. So for this first one over here, there's like 8 choices. You can end at the same point that you started. You can end at the next one over, the next one over, or like so on and so forth until the very end. So for 1 through 8, right, there's 8 choices for j if I is equal to 1. There's 7 choices for j if I is equal to 2, and so on and so forth until I is equal to 8. Then there's only 1 choice for j. It has to be 8 as well. So we think, I mean, you've seen this before, right? So the sum from I goes from 1 to n of I, it's roughly quadratic. So there's roughly O of n squared different choices of I and j. Okay? So you have to try out all of these. And for each value of I and j, how long does it take to calculate? Well, you have to sum up like j minus I plus 1 different elements. Okay? So really, you have like depending on how far I and j are, you could take more time. It's not like each one of these sums takes constant time to evaluate. In the worst case, you sum from beginning to end, which takes time linear in n, which is the number of elements. So I guess we can, to think about the runtime in a rough sense, we can think like an average array here would be roughly like half the elements. Okay, so it's roughly each sum takes on average about time proportional to n over 2. And then so the runtime of this algorithm, the brute force algorithm, is n cubed, which is not the worst thing in the world, but it's still like it's polynomial time, but n cubed is. Oh, yeah, hello? Do you have a question? I guess not. Okay. All right, so yeah, okay, we'll keep going. So we can do better, okay? So let's think about how we might do it using divide and conquer. So what is like the typical approach to divide and conquer? You split it into subproblems, and then you solve the subproblems, and then you stitch those subproblems together. So what can we do here? With divide and conquer, we can split this into two arrays. Okay, so either the maximum subset or substring sum is in the array is either in the left half or the right half, or it overlaps between halves. Those are the only three options. Okay, so it's either in the left half, it's either or in the right half, or overlap. So these are the only three options. That is, there's some in the, like, it's an array which includes the middle. Okay, so think about how you might deal with that case. So the recurrence relation here, I won't go too much into the algorithm in depth. The idea is this takes T of n is equal to, how many subproblems do we have? We have a left half and a right half. So two subproblems, each of size n over 2, because we split the array in half. And now let's think about this case over here, the overlaps. So if it's an overlap, it must be like, it must include the middle somewhere. So the idea is you include the middle, and then you grow it from the left, and you grow it from the right. And then you basically only add an element if adding it either increases the sum, or adding it and then some more elements would increase the sum. Okay, I'll let you think about that more in detail. Like, think about how you might implement this case algorithmically. But the idea is that growing this array from the middle, in the worst case, would just take the entire length of the array. So the worst thing is O of n time. And so does anyone remember the solution to this recurrence? We've seen it so often. This 2t of n over 2 plus O of n. This is like merge sort, right? So what is the runtime? That's right, it's n log n. So that's a lot better than n cubed. And log n is generally small for a lot of things, but we can do better than log n or n log n. Okay, I'll claim that we can do a linear solution, and we're going to do that using something called dynamic programming. Okay, so dynamic programming. I'll tell you a fun story about dynamic programming first, though. So dynamic programming, it got its name because it was in the late 1900s. Computer science needed more funding, okay, especially theoretical computer science. People weren't really getting funding for that. So the guy who invented dynamic programming was like, I'm going to give this thing the most buzzwordy name I can. So it's really just a technique for designing algorithms. But he decided to call it dynamic programming so that it would sound cool, and then he would get funding for it. So I always think that's a pretty cool story. And it's a very, it teaches an important lesson to, even if you do good research, you have to market it well. So anyways, this is what dynamic programming is. It's a concept of solving problems by storing solutions to subproblems and then building things from those solutions. It sounds a lot like divide and conquer, but I will say it's a bit of an extension. Divide and conquer, you split into, you branch out into smaller subproblems and you combine them. Here you build solutions to problems by first constructing the subproblems and then building it from the bottom up. Okay, so let's, I'll claim that there are 4 steps to devising a good dynamic programming algorithm. So the first step, okay, is to define your subproblems. This is like defining your variables in your recurrent relation. So define your subproblems. This, okay, is really about, I would say this is about 45% of the work most of the time. And second step, okay, is to take these subproblems and then to build, actually not even 45, this is like 50%. Big difference, I know. But you take these subproblems and then you build like a recurrence relation out of these subproblems. And that's about 40% of your work. I mean, these are all like rough numbers, you know. I'm just trying to take the point that if you define your subproblems properly, the rest of the problem simplifies considerably, okay? So a lot of the battle is won at the very first step. You build a recurrence relation out of these subproblems. So how does a super problem depend on its subproblems? That kind of relation between subproblems is something you want to think about. And the third thing is you want to devise a method to fill out. So at this point, you're going to be maintaining like a table or array or a list, however you want to structure it, of subproblems and their solutions, okay? And at the beginning, everything will be empty, and you want to try to figure out how to fill that table out, fill out the table of subproblems. In particular, you want to go about this process in a way that you don't ever require an answer to a subproblem that hasn't been solved yet. So if you need a subproblem for a future thing, it's already been solved by the time you use it. Okay, so right, so that should remind you of something from maybe week 2 or 3 of the class. So start thinking about what that sounds like a dependency of these subproblems. But the fourth and final step is to, from your table, choose an answer. And we'll see what that means shortly. But just because you've solved the subproblems doesn't mean you're done. You have to combine those subproblems in a way. Sometimes it's just taking the biggest subproblem, like the final answer subproblem. Sometimes it's taking the sum of subproblems. Sometimes it's taking like the max or the min. Sometimes it's a bit more complicated than that. But this is also important. You have a table, you got to pick something from that table or like use that table to find out your final answer, okay? So, right, so let's look at an example. So we'll go back to this problem over here about maximum sum of a substring. So what could be a candidate subproblem here? Any ideas? What could be a subproblem? So we can say M, we'll call it M for like, because we'll take the first letter of the problem. M of I comma j is going to be the maximum sum of an array between I and j. So what this is saying is it's just an array that's constrained between I and j. It doesn't have to start at I and end at j. It just has to be somewhere in between. Now there's an issue here. How would you construct M of I comma j plus 1 from this? It's not immediately clear, right? Because just because something is between I and j doesn't mean it starts at I or it ends at j. So you don't know if this maximum thing is something that ends at j. So you don't know if you can just add on the j plus 1th element to it to create the maximum sum from I to j plus 1. Okay, so there's not enough information here. We don't know if it actually ends at j, so we can't tack anything onto the end. So, okay, we'll say, let's give some more information. Maximum sum of an array that actually starts at I and ends at j. So this is a candidate subproblem, and it's clear how you can, it might be clear how you can like grow the next element from this, because you can just add the j plus 1th element to the end, but there's another problem here, okay? And the issue here, okay, is that this isn't really like a subproblem. Like this is literally just the sum of these elements. So these subproblems help you calculate the sum, but that's not necessarily equal to the maximum sum of an array. So it's like this maximum is doing absolutely zero work because there's only one subarray that starts at I and ends at j. You're not really taking the maximum over anything, okay? So we need somehow more information than it's between I and j, and it starts at I and ends at j. Okay, so one of these gives too much information, one of these gives too little information. So we need some kind of compromise here. Does anyone have any suggestions? I'll give you a hint. Maybe think about shaving off one of these indices. Any ideas? Maybe instead of saying it both starts at I and ends at j, we can say, yeah, it could start at I, but needs to end at j. Actually, I'll just take a little bit of that. Yeah, we could say it starts at I, for example. I will say, I think it's a bit more natural to say, so let's X this out to to express our annoyance at how specific the subproblem is. Instead, we'll take the subproblem M of j, the maximum sum of a subarray that ends at j exactly. Okay? Now, now we're going to add a bit of a caveat here. Okay? What if like the jth element is like negative, for example? What if this sum is negative? Well, notice in this problem, okay, the subset sum could be empty. Like the empty set is a valid substring of an array. So the idea is in any of these subproblems, if like we're getting something that's less than 0, we can always just take the empty set, and the empty set by definition has sum 0. Okay, it's also, you'll also hear that called the empty sum. Okay, so if this maximum sum is negative, we just take the empty set. And this is a bit of a technicality. While the empty set doesn't necessarily end at j, we'll just say it like starts at j plus 1 and ends at j or something. Okay, we'll say we're going to cut off like the running sum at this point, and we're just going to start anew at j plus 1. If it is the case that like the maximum subarray sum that ends at j is always going to be negative. Okay, in particular, look at this example. So 1, negative 100, 5. So anything that ends here, right, will be negative. So instead of that, we'll say, well, we want to build like the subarray sum that ends at this point based on the answer to the previous one, but we don't want to include this 100. So what we'll do is we'll just say, okay, we will not include this 100. We'll just say the solution to the subarray that ends at 2, we'll just say it's the empty set, and we'll start from scratch every time we're going to build from that point. Okay? Does that make sense? That was kind of confusing. So don't feel afraid to ask any questions. Even if you think that other people didn't think it was confusing, it's always fine to ask questions. Okay, so our subproblem is going to be M sub j, or M of j is the maximum sum of a subarray that ends at j. Okay? And if the sum is empty, we'll just say it's the empty set. So M of j, max sum that ends at j. So that's the first step. We've defined the subproblem. Okay? What is the second step? We need to build a recurrence relation. Okay? So how is M of j plus 1, or what does M of j depend on? Well, there's choices here. Whenever you're building these recurrence relations, you think of a choice, okay, with the particular element that you're adding on. With this element a sub j, you either include it in the maximum sum that ends at a sub j, or you don't. In the case that you don't include it, right, if it ends at j and you don't include the jth element, then that's the case where we take the empty set. Okay, so what happens if we do include the jth element? How is it dependent on the previous subproblems? The maximum subarray sum that ends at j is the maximum sum that ends at j minus 1 plus the jth element. Does that make sense? Like if we include this jth element, then we had also better include the maximum subarray of everything that comes before it. Okay, so it's M of j minus 1, the solution to the subproblem, plus the jth element. Okay, let me create some space here. We'll see why in a bit. Okay, but what if it's the case that this is 0 or less than 0? Well, then we don't want to include a negative sum at any point. That's just, you never ever need to include a negative sum because you can just always consider the empty set. So in the case that this is less than 0, we'll just replace it with 0. So either this is greater than 0, or we'll say the empty set ends at j. Okay, so it's the max between the maximum sum that ends at j minus 1 plus the jth element, or just the empty set. So either we include the jth element, or we don't include the jth element. Okay, so that logic is kind of common. Like you either include this element or you don't. Does that make sense? Okay, so I bet that was a Discord notification. Okay, so all right, so let's talk about how we can devise a method to fill out the table of subproblems. So what I said earlier, what I alluded to, you don't want to rely on a subproblem that hasn't been solved yet. What does that sound like? Like what concept does that sound like from earlier in the class? Anyone have an idea? Think about a dependence between objects and you want to like go about them in a particular order. I'll give you a hint. It starts with topological. Yeah, topological sort. Okay. So that was a very good hint, but here's the idea. Okay. So we have the subproblem 1, where j is equal to 1, subproblem 2, subproblem 3, and so on and so forth. I'm going to draw an arrow from one problem to another. I'll draw a problem from arrow from 1 to 2 because problem 2 depends on the solution to problem 1. So we must solve problem 1 first. Problem 2 depends on problem 1, problem 3 depends on problem 2, and so on and so forth. And so this is a DAG. This is a directed acyclic graph. It's directed because there's directional dependencies, and it's acyclic because if it wasn't, then we'd have a problem. So what if we had to solve 3 before solving 1, indicated by this arrow over here? Well, if we solve 1 first, then we'll need the solution to 3, so we can't do that. But if we solve problem 3 first, then we'd need the solution to problem 2, which requires the solution to problem 1. Either way, we rely on a problem that has not been solved yet. Okay, and so therefore, in any like recurrence relation, we must require that it's a DAG. Okay, a directed acyclic graph. So the moral here is that your subproblem dependency graph everyone understand what I mean when I say subproblem dependency graph? You draw each subproblem as a node, and you draw a node between an arrow between node I and node j if you must solve subproblem I before you solve subproblem j. So this graph must be a DAG. Otherwise, there is no valid way of solving this without like relying on an unsolved problem. And then we're gonna have a base case here. I'll draw it as a square. So like, what is the sum of something that's like ends at 0? Well, this is just like the empty set. So the sum is equal to 0. All right. And so how do we fill out these things in order? Well, we just go for I equals 1 to n, or for j equals 1 to n, and then just this formula. And we will always be guaranteed that when m of j is being considered, m of j minus 1 has already been solved. Okay. So that's important. Just building subproblems that go about this order. And now you can see why defining the subproblems is so important, because like you got to define them the right way, or else. Okay, let me turn on my brightness because my battery is draining. But we have to define subproblems that, like, one, don't include too much information or too little information, or like don't like require cyclic recurrence relations, right? So you have to define your subproblems very carefully. Okay, absolutely spend a lot of time thinking about these things. If they can be optimized, if you need to add indices, if you can build recurrence relations out of them, if you can remove indices, if you're including too much information, because that'll help your runtime. The more indices you add in your subproblem, the higher the dimension of your array is going to be. Here, there's only one index, so this is like a single dimensional array. But in the future, you'll see subproblems that have 2 indices that are like 2-dimensional arrays that are going to be quite troublesome to deal with. So make sure you don't include any extra information. So that's what I mean when I say define your subproblems very carefully, because that is absolutely the crux of dynamic programming: the subproblems and then the recurrence relation. Once you define the subproblems, everything else will fall into place. Hopefully, I mean, not always, but generally that's how it is. Okay. So now let's choose an answer. So now at this point, we have the solution to m of 1. We have the solution to m of 2. We have the solution to m of 3. And we have the solution to all of them up to m of n. So which one of these things do we choose? M of 1 is the biggest subarray sum that ends at 1. M of 2 is the biggest subarray sum that ends at 2. Which one of these is the biggest subarray sum, period? Not necessarily M of n, because remember, the biggest subarray sum doesn't necessarily end at n. It could end at any of these, but we want to pick the biggest one. So we take all of these things. Yes, so Tushar is correct. We take the maximum. Okay, so you take the maximum of all of these, and that gives you your final answer. Okay, so here, the final solution is not just one subproblem, it's them combined in some way. Like I was alluding to earlier, the maximum is often a common way to combine subproblems. Okay, so let's analyze the runtime. When you analyze the runtime, okay, so I'll add another moral here. There's a lot of morals today because dynamic programming is, a very didactic subject. So the moral here is for runtime. Well, let's talk about correctness first. How can you argue this is correct? We just claimed that we had a recurrence relation and we filled things out in order, and we proved that we never really look at something that hasn't been solved yet. How do we argue that the thing is correct? Well, how do you argue the correctness of a recurrence relation? You build it up, right? Induction, yes. Michael is correct. You use induction. Okay, so for correctness, you use induction to prove the recurrence relation. There's not much more to say about correctness here. If you prove the correctness of the recurrence relation, and you argue that like this final process of selecting the answer is correct, then you are done proving correctness of dynamic programming. Okay, so generally that's not the hardest part of dynamic programming because it's formulaic how you prove it. You go by induction. I'm not saying induction is formulaic, but like you get what I mean. There's a standard technique to prove it. Unlike greedy algorithms, like sometimes swapping algorithms work, sometimes staying ahead works. With dynamic programming, you prove by induction that the recurrence relation works. And for runtime, what do you do for runtime? You count how long it takes to fill out the table. So how long does it take to fill out the table? So basically you have n elements in this table, right? You think about how much time it takes to fill out each one, and then you sum them up. In general, that's what you'll do. You'll have an array. Not every subproblem will take the same amount of time in general. Some will depend on the size of the subproblem. Like some will be the max from like this j minus 1 might be replaced with from I equals 1 to j minus 1 or something. And then it depends on j different subproblems. So that's not true in general, but here it's the case that each subproblem takes constant time to solve. And there are n subproblems, so it takes time n to fill out the table. But you also have to add the time to combine the answers. What I mean by that is the time it takes to choose the final answer based on your filled out table. That also takes time O of n in this case, because you're taking the maximum across n elements. Okay, so you're taking O of n time to fill out the subproblem table. And then amongst those subproblems, it takes time O of n to pick the right one. So therefore, it takes time O of n in general, which is a small improvement over n log n. Okay. Does that make sense? All right. So with that in mind, I would like to give you all another practice problem that's not on the worksheet. So would you all like a difficult dynamic programming problem and watch me walk through it? I feel like you would. I feel like maybe I'm just choosing for you because I like difficult problems. But I mean, this is a yes, law. Okay. So I mean, I will say this is probably a common interview question. So maybe that gets you all more excited for it. Dynamic programming is ubiquitous in interviews. If you can get good at dynamic programming, that elevates you as a programmer so much. I say this as someone who hasn't programmed anything in years, but I really do think it's a useful tool for interviews. Okay, so right. So this problem is called string shuffling. What is string shuffling? So let's say you have a string X, and let's say, for example, it's equal to cat, a string Y, which is equal to dog, and you have a string Z, which has as many characters as X and Y combined. So it's supposed to be like derived from X and Y in a certain way. So basically, you take the strings of the characters of X and Y in order, but you might like take some characters of X and then some characters of Y, then some of X again and some of Y. Like you can alternate between them. So for example, CADOTG, CADOTG is a valid shuffling because you're taking the letters of cat in order and you're taking the letters of dog in order, but you're shuffling them in some way. Okay, you can think about it as having two decks of cards, and you can at any point take the top of each one and put them in your new deck, and like you're like shuffling your deck that way. Okay, so for example, this is not a valid. Okay, so dog cat. So this is cat.g is valid. Dog cat is also valid. Cat dog is also valid. What is not valid? Can someone give me something that is not valid here? How about cadgato? Why is this not valid? Well, you'll notice that the G and the O are out of order. So the O comes before the G in dog, but it comes after the yeah, and tack god is also a tack dog. And yeah, okay. I like these examples. This is a very funny problem. But yeah, so can we see like what the correctness of this is? So this is not something that's like a number. This is like a true or false type problem. It's a Boolean problem. So we'll see how to build subproblems based on like truthy or falsy values. Okay. So let's think about some subproblems. Now let's brainstorm. Okay. So the first idea for a subproblem that we might have is I'll again use S because I'll just pick the first letter. If you're struggling, just pick the first letter of the problem. Unless it's like O, then don't use O because you'll get it confused with big O or something. Then pick like the second letter. But that's how I like to pick the subproblems for. So let's say S of, oh yeah, by the way, let's say X has M characters and Y has N characters. Okay, this absolute value means the number of characters or the size of the set or whatever. So let's say S of K is equal to whether the first K characters of Z can be shuffled from X and Y. So if S of 3, for example, would be either the first 3 characters of Z come from the first 3 characters of X and the no characters from Y, or the first 2 characters of X and the first character of Y, or 1 character from X and the first 2 characters of Y, or no characters from X and the first 3 characters from Y. So that's what S of 3 would be. Okay. Now, what is the problem with this subproblem? I'm already telling you that it's doomed to fail. Well, how would you build K plus 1? You'd have to think about a lot of things here, right? K plus 1, okay, the next element of Z, well, it could come from X or Y, right? And I don't know, like, if S of K is true, I don't know how much of this first K characters is composed of X and how much is composed of Y. Oh, the question here is, what are we trying to find out? We're not trying to find out all possible shufflings. We're trying to take an X, Y, and Z and see if Z can be validly shuffled from X and Y. So this is a true or false statement. To find the valid shufflings, you should think about how to do that as well. That's a very combinatorial problem, but I'll claim that you can solve it using, you all know stars and bars? Yes. You can solve it using stars and bars. If you haven't heard about that, don't worry. That's not even close to being in scope for this class. So, but we're trying to find a true or false thing over here. Okay. So what can we do? Instead of just S of K, what can we do here instead of just having one index? Remember, sometimes you have too little information in your subproblem. How can we make amends here? Instead of S of K, we can do S of. Any ideas? I will not progress until I get an idea. Yeah, okay. What is S of X comma Y? What is your idea for that? What does that mean?
I was thinking like maybe the first K characters of X and Y, but I'm not sure.
Oh, the first K characters X and Y each. Yeah, that's one. My goodness. That's one possible solution. But how about we do this instead? Okay, we do I comma J. So we get whether the first I plus J characters of Z can be shuffled from the first I characters of X and the first J characters of Y. Okay, so here we're maintaining information at every point in the subproblem of how many characters come from X and how many characters come from Y. So for this particular problem, okay, let's say Z is cat, dog. So S of 3 comma 0, or yeah, S of 3 comma 0 would be correct. Why is that? Because the first 3 plus 0, the first 3 characters come from the first 3 characters of cat, right? But S of 2 comma 1 is false because the first 2 plus 1 equals 3 characters of cat dog do not come from the first 2 characters of cat and the first character of dog. That would be CAD or CDA or DCA. It would certainly not be cat. Okay? Does everyone understand our subproblem? Okay. So now we're going to the next part to build the recurrence. So S of I comma J. So if S of I comma J is true, then what must be true about the I plus jth character of Z? It must either come from X or it must come from Y. That's true about every character of Z. But we have this information about the first I characters of X and the first J characters of Y. So therefore, the I plus jth character of Z must come from either the exactly ith character of X or the jth character of Y. Does that make sense? Because if it came from an earlier character, then it would be out of order pretty much, right? Does that make sense? So either it's the case that the I plus jth character comes from X, in which case it's the ith character of X, or it comes from Y, in which case it is the jth character of Y. So let's think about the first case where it comes from the ith character of X. So we require that X of I is equal to Z sub I plus J. Okay. And now it's certainly true that the I plus jth character can come from the ith character of X. But what must be true about the I plus J minus 1 characters before Z sub I plus J? What must also be true? That they can be shuffled from how many characters of X? I minus 1, because we use the ith character of X to add this next element onto Z. So the previous I minus 1 elements of X must be used to shuffle the previous I plus J minus 1 characters of Z. And we haven't used Y in this new kind of addition to Z here. So this J remains the same. Okay. So it must be the case that this and this are true. This mountain over here is the logical and symbol. I assume you've seen that before. So these both must be true. Okay. This is one case that the I plus jth character comes from X. What if it comes from Y? What does that look like? So either this is true or this is true. So what should I write here? Y of J So either the I plus jth character of Z comes from Y, okay? And then what else must be true? The previous I plus J minus 1 character from Z must be coming from from what? We didn't use X here. So how many characters of X remain to shuffle the previous elements? I. And then we use the jth character of Y. So the previous J minus 1 characters of Y must be used to shuffle the previous ones. Does this make sense? And this is the recurrence relation. Okay. This is the case that it comes from X, and this is the case that it comes from Y. So how long does it take to fill out this recurrence relation for every pair of I and J? For one particular choice of I and J? Well, all these are constant time operations. There's a table lookup. There's a couple of table lookups, actually. There's some comparisons. There's some Boolean operators. But these are all constant time operations. And so therefore, it takes constant time to fill out each element of this array. How many elements of this array are there? Well, there's m choices for I, and there's n choices for J, leaving a total of mn choices for the table. So the table is of size mn. Now, how do we fill them out, though? That's the tricky thing, right? So let's draw the graphs. Let's get some space here. So let's say I goes up this way. And let's say J goes up this way. Okay, J is increasing from 1 to n, and I is increasing from 1 to m. So each subproblem depends on the subproblem with 1 less I and 1 less J. Okay, but you fix the opposite coordinates on each respective subproblem. So in this graph, each subproblem depends on the problem immediately to its left and immediately above it. Okay. Do we understand this recurrence graph over here? So the left, the arrows going right they correspond to this case over here. I don't know if you can see that. That's an awful color. But and the arrows going down correspond to this dependence on this subproblem over here. Okay. So right. So we draw this. Is this a DAG? I mean, yeah, because otherwise I wouldn't be telling you this. But like, why is it a DAG? Well, realize to have a cycle, you must have an arrow that goes up, because all of these arrows go down and to the right. So you must have an arrow going up and left, but no such arrow exists. Okay. So I guess you don't really have to, you don't have to like topologically sort the DAG to show that it's, you know, a DAG, but like you can just argue that at any point, if I solve all the I and J that come like before, then I'm done, or I don't have to worry. Okay, so what is one way we can traverse this? Let me change the color. So I like this color. I'll use this one. So can we traverse things in this order over here? We can go row by row. Can we do that? Well, let's think about any time we solve this subproblem. Whenever we solve this subproblem in blue over here, we've solved the previous row. So this dependency over here is good. Okay. Now, what about the things to the left? Just the element immediately to the left. Well, each row, we go from left to right. So we can also be sure by the time we reach something in a particular row, we have solved the dependent subproblem within the same row. Okay, or the problem that it depends on. So this is a valid method of traversing this table. Okay, it's a valid topological sort to go row by row. How about column by column? Does that work? Does column by column work? What do you think, chat? Chat? RIP. You're probably so confused. Okay, I mean, okay, fine. I'll give you all a break. So the chat, the going column by column works as well by symmetry, right? Because like I and J shouldn't really, it shouldn't really matter whether you go by I or J first. But if you go column by column from top to bottom, and then like you go left to right columns, well, you can be sure that the previous column has already been solved. So the left dependency is good. The top dependency is good because you go from top to bottom. Okay. So I guess you may not like this may not be incredibly obvious here right now, but the more you practice and the more you do these things, the more it'll be clear that the order you have is also valid. So by the way, another valid ordering, which is like kind of extra, but also kind of cool, is you can like go diagonally like this. Okay. And so, yeah, so that's how you might solve this subproblem. So I just a couple of notes about the ordering here. So again, it takes OMN time. Which subproblem do you pick in the end? Well, you want the first M characters of I or X and the first N characters of Y to be shuffled into Z. So you, in this case, you do end up picking the problem that's on the bottom right. So the final subproblem. In other words, you pick S of M comma N. So it takes constant time to choose the final subproblem. It takes MN time to fill out the table. So MN is your final answer in terms of your runtime as well. Okay. So if you want an extra challenge problem on this particular like exercise, at the end of my like discussion recording on Wednesday, I gave an extra problem where you can save some space on this. So instead of filling out the whole table, you can just fill out a row by row. So think about how you might do that. Okay, and so look at the Wednesday discussion recording for more details. Other than that, do we have any questions? I think we went a little bit over time, but at least we got this problem done. Any questions? No? All right, I'll stop recording. Okay. Anyone want to ask anything off the recording? Oh, wait, no, I didn't stop the recording. Okay.